15.6 covers the application of equilibrium constants. The reaction quotient is Q, and Q gives the same ratio as the equilibrium expression gives, but for a system that is not at equilibrium. So what that means is when you set up your expression, it's just like how you set up K with your concentration of your products over the concentration of your reactants. To calculate Q, one needs to substitute the initial concentration of your reactants and products into the equilibrium expression. So there is a difference between Q and K. Q is like K, except it is the same expression, but not when the system is at equilibrium. So keep that in mind. Just like I said, it's written just like K. So if we look at the example of N2O4, is at equilibrium of 2NO2. We start the reaction with just N2O4, and there is no NO2 at first. So that means the reaction will only proceed towards the NO2. It is the only way it can go. Eventually, when there is NO2, the reaction will begin to change back towards the N2O4. Then the N2O4 will go back into the other direction, and it will change back into the NO2 and so on. So this Q value would tell us which direction the equation needs to go or the reaction needs to go in order to reach equilibrium. So the reaction would need to first go towards the products to reach equilibrium, because in this example here with the N2O4, there's only N2O4 to start with. We can calculate Q, then compare it to the known K value. Then we can determine the direction a reaction needs to go in order to get K. So for Q, you use the initial concentration, not the equilibrium concentration. So right here it says your initial concentration. Note that Q equals your equilibrium constant only at equilibrium. So Q equals K only at equilibrium. If Q is less than K, then the forward reaction must occur to reach equilibrium. Q increases until it equals your equilibrium constant. That's a typo, that should be until. If Q is greater than K, then the reverse reaction must occur to reach equilibrium. Products are consumed, reactants are formed. Q decreases until it equals K, or your equilibrium constant. So if Q equals K, the system is at equilibrium. So that's pretty easy to remember. If Q is greater than K, your equilibrium shifts back towards the left to form more reactants until Q and K are equal to one another. And if Q is less than K, the reaction needs to form more products until it reaches equilibrium. Sample exercise 1510 is on page 628. It says at 448 degrees Celsius, the equilibrium constant, Kc, for the reaction H2 plus I2 produces 2HI is 51. Predict how the reaction will proceed to reach equilibrium at 448 degrees Celsius if we start with 2.0 times 10 to the negative second moles of HI, 1.0 times 10 to the negative second moles of H2, and 3.0 times 10 to the negative second moles of I2 in a 2-liter container. Q equals, in the end, 1.3, so the reaction will proceed from left to right. But how do we get to the 1.3, and how do we know it's going to proceed left to right? So the first thing we want to do is we want to look at what we're given. So we're given that K is equal to 51, and we need to be careful when we plug in our values for Q that we use a concentration rather than our number of moles. Since we're given the number of moles and we're given 2 liters for the container, we have to divide our moles by our 2 liters, and that will then give us our concentration. Okay, so we're going to take the concentration of HI, which is 2.0 times 10 to the negative second moles, divide it by 2, and that will then give us our molarity, 1.0 times 10 to the negative second moles per liter. We also have to do this for H2 and I2, divide by the 2 moles. This is going to get us into our concentration of molarity. Since we're given the initial concentration to start with, so think about, if we look here, it says, predict the reaction that we start with. So we know that this is meaning that we're going to work with initial. We're working with Q. Our next step is to write our Q expression. It's just like writing the equilibrium expression, but we're going to be plugging in the initial concentrations instead of the equilibrium concentrations. So here's the equilibrium expression. We use our balanced equation. So our products are going to go on the top, the concentration of HI squared over the reactants, the concentration of H2 times the concentration of I2. And next we're going to plug in the initial concentration, so these numbers here, into our equilibrium expression. So now we have plugged in the values into our expression for the HI, the concentration or the molarity for HI, squared the concentration of H2 and I2. And notice that I did not write any units because the values have now become activities. So we're going to go on and solve. So then we're going to square this, multiply, and divide, and we're going to finally get to the answer that Q is equal to 1.3. And we said that K was equal to 51. So Q is a lot lower than your equilibrium value. So that means our Q expression needs to get bigger to reach equilibrium. The only way to make it bigger is if the HI concentration, okay, increases and the H2 and the I2 decreases. Then this will make Q bigger, or make it closer to K until Q equals K. So basically this is telling us, based on our starting amounts, which direction the equilibrium will move to get the reaction at the more correct concentration. So that means that the reaction is going to, let me go back here to our balanced equation here, that means that it's going to basically shift in this direction towards your products to reach equilibrium. Thus, we're going to need to make more HI to reach equilibrium, and we're going to have more products. So that's why we're going to say it proceeds from left to right. So let's look at this graphically. Back in a future unit, we had looked at the graph here, in which we had concentration over on this side. And then this was the time. Or we could say the reaction process, okay? So if we look at this, notice we're not going to start with HI, our product, at 0, okay? Because we were given some initial concentration. So we're going to start HI somewhere about here. HI is going to increase, and then it's just going to kind of level off. That's supposed to be hopefully a straight line there, okay? It's going to be leveling off there. Okay, so it doesn't start at 0. HI, we did have a beginning concentration. The concentration of HI is going to increase until it starts to level off. Then if we look at the concentration of I2 and H2, we did start with a large concentration of HI. So it's going to look something kind of like this. It's going to decrease and drop. H2 actually was just a little bit lower than your products, HI, so it would kind of do something like this and then level off. Okay, so this is going to be HI. This is going to be I2 and H2. Okay, so notice that HI is increasing until it levels off. That means that our products are increasing, which is HI, and that our two reactants, I2 and H2, they are decreasing, and they will eventually level off. So the endings may not be exactly correct here. We would have to do an additional calculation, but you kind of get the idea graphically if we're looking at this process. Okay, we're going to quickly just look at the practice exercise 1510. It's worked very similar to the sample problem we just worked out. We're looking at the equilibrium equation where 2SO3 is at equilibrium for 2SO2 plus O2, and the value for Kp is 0.338. We need to calculate the QP and predict the direction in which the reaction will proceed toward equilibrium if the initial partial pressures of the reactants are 0.16 atm, 0.41 atm, and 2.5 atm. So I just quickly want to look at how we would set this one up. It's very similar. The first thing we would need to do is write our equilibrium expression for this, in which so this is what the equilibrium expression would look like. We have the pressure of SO2 squared times the partial pressure of O2 over the partial pressure of SO3 squared. Then we would plug in our values for the partial pressures of our products and our reactants into our expression, our Q expression. Okay, notice that I did not plug in atmospheres. I left the units off because these are now activities. Plug in and solve. So we have 0.41 squared times the pressure, 2.5, and then we're going to square this and then divide. And our Q ends up being 16. So in this case, Q is actually going to be, let's see, what is our K? K is 0.338. So Q is actually greater than K. So that means that our reaction needs to proceed right to left. We need to make more of our reactant, the SO3. Okay, so think about if I want my Q to be smaller in this example. So let's look at the graph again. Concentration over here, time here, okay, or how the reaction would proceed. So since we need to make more SO3, SO3 actually would be right about, we're just going to say here, and it would have to increase and then level off. Okay. Because let's see, that is, it's our lowest of our 0.16, excuse me, 0.16, so that's why it's going to be the lowest on our graph. Then we're going to have SO2 is going to need to decrease. And then O2 actually had the highest concentration here. So it also would need to decrease here. Okay. So if we want Q to be smaller, in this example, Q is bigger than K. So at this point, to get it smaller to reach equilibrium, we need to have the concentration of our reactant will need to increase in order to make the Q value smaller. Then the concentration of the products need to decrease. So notice the O2 and SO2 have decreased. And then the reaction needs to also decrease. Or excuse me, the concentration of your products need to decrease. Then the reaction is going to basically shift. If I can go back to my equation page, here we go. That means that the reaction is going to shift in this direction. Okay. So it's going to actually shift towards your reactants. Okay, now we're going to look at sample exercise 1511 on page 629. It says for the Haber process, we have N2 plus 3H2 produces 2NH3. Kp is equal to 1.45 times 10 to the negative fifth at 500 degrees Celsius. In an equilibrium mixture of the three gases at 500 degrees Celsius, the partial pressure of H2 is 0.928 atm, and that of N2 is 0.432 atm. What is the partial pressure of NH3 in the equilibrium mixture? So now we're going to go back and focus on to K. So we're going to be looking at more equilibrium type problems. In this problem, we have K solved for us or given to us, and this is where we're going to need to basically find one of our concentrations. In the problems in the past, we were solving for our equilibrium constant, okay? Now we need to find the equilibrium concentration or the equilibrium partial pressure in this case because we're working with pressure. So the first thing we're going to need to do is write our equilibrium expression. So this is the expression. This would be Kp equals the partial pressure of NH3 squared over the partial pressure of N2 times the partial pressure of H2 cubed. Since we were given the equilibrium partial pressure of two of the gases in the reaction, and we were given the equilibrium constant, we're going to now solve for the partial pressure of one of the other gases. So the first thing we're going to do is we're going to plug in our given values into our equilibrium expression. Okay, so our Kp is 1.45 times 10 to the negative fifth equals NH3. We were not given the partial pressure, so that's what we're solving for, squared over the pressure of N2, which is 0.432, times the pressure of H2, which is 0.928 cubed. So when we cube this, multiply this, we're going to get, okay, so now we're going to get 1.45 times 10 to the negative fifth equals x squared over 0.345. So we need to move the 0.345 to get x squared by itself. So now we're going to get x squared equals, and then we would go on and multiply our answer, the 0.345 times 1.45 times 10 to the negative fifth, and that is 5.01 times 10 to the negative sixth. And then to get x, because x is squared, we're going to do the square root of each side. And when we do that, x will give us a positive and negative value of 2.24 times 10 to the negative third. And this would be atmospheres of NH3 for the partial pressure of NH3. Okay. Now remember that we're going to get both a positive and a negative value. We're going to ignore the negative value because we can't have a negative pressure. So our answer is actually going to be a positive 2.2 times or 2.24 times 10 to the negative third. I skipped over a couple of the sample problems because I don't want this video to get too long, but they're very easy to work out. So let's go on and look at the last sample exercise 1512. This is actually on page 629. So we have a 1 liter flask is filled with 1 mole of hydrogen gas and 2 moles of I2 gas at 442 degrees Celsius. The value of the equilibrium constant, Kc, for the reaction, there's our equilibrium reaction, at 448 degrees Celsius is 50.5. It wants to know what are the equilibrium concentrations of H2, I2, and HI in moles per liter. Okay, so notice we're given 2 initial concentrations. We have 1 mole and 2 mole in a 1 liter flask, and that's going to equal the concentration in the 1 liter flask for our given values of Kc. Since we don't know any of the equilibrium concentrations at this point, this means like from the last section, we were given the initial concentration and the final concentration to figure out the change in our ice table. Let's see if went too far. Here's my ice table. Okay, so notice here that we're only given the initial concentrations. We're not given a final concentration here within our ice table. So we're also going to assume in our ice table that we're given 0 HI to begin with. Okay, because we're only starting with H2 and I2. Okay. We don't know how the reaction has changed. We do know, based on the stoichiometry, though, how they will change relative to one another. Okay, so that means the only direction this reaction can go will be towards the products in that direction here. So the reactants are going to decrease. So that means our reactants are going to be negative in value and our products are going to increase. Otherwise, we wouldn't have a reaction occurring. Okay. Okay, so that's why I have right here our negatives. Hydrogen must decrease because the reaction is moving towards your product side. I know hydrogen will go down by X. Okay, based on the stoichiometry right here, it's 1, so that's why I'm just going to have an X here. I know that my I2 is also going to go down, so that's why I have a negative value here. And because this is a 1-to-1 ratio, I am also going to give this a 1x. So I'm going to use the stoichiometry here to help set up the x's. Then I'm going to look at my product. My product is going to be positive because I'm going to be making it. I'm going to look at my equation stoichiometry. Since there's a 2 here, it's going to be plus 2x. That means HI will increase 2 times because of the coefficient of 2 in front of the HI. Okay. Now I can go on and plug in. I'm going to make this 1 minus x, 2 minus x, and then this is just going to be 2x. Okay, so just go on and drop that down. Next, I'm going to write my equilibrium expression for my equilibrium formula. So I have the concentration of HI squared over the concentration of H2 and the concentration of I2. And then I'm going to plug in my values from my ICE table. So I have 2x squared over HI was 1 minus x, and I2 was 2 minus x. So that means that we're going to have to factor or use the FOIL method, okay? So basically where we're going with this is we're going to end up with a quadratic equation, and we're going to have to use the quadratic formula to solve for this equation. If you need any refresher on the quadratic equation, just look in the back of the book on page 1055, and that will kind of help guide you along if you need more information. Okay, so when we FOIL, that means we're going to multiply the first terms together. Okay, then we're going to multiply the outer terms together. Okay, so F for first terms, O for outer terms. Then we're going to multiply the inner terms together, so our two inner terms for I. And then for L, we're going to multiply the last terms together. Okay, so when we factor, we are now going to get x squared minus 3.0 x plus 2. Okay. And essentially what we're going to do is we're going to have to multiply the 50.5, okay, because we were given that as our KC. When we do this and we multiply by the 50.5 by the bottom section here, so we're referring to this bottom section, we're going to now have 4 x squared is going to be on the other side. Okay, so we're going to end up with the expression of 46.5 squared minus 151.5x plus 101.0 equals 0. So now hopefully you can kind of see where we have the A, B, and C to fill into our quadratic formula. Okay, so again, the quadratic formula, excuse me, is on page 1055 if you're not sure where the formula is. So you can take a look at that, in which they've already plugged in our values here. And notice the 2x value means we're going to have a positive and a negative in this case. But again, we're going to ignore the negative. And basically what we're going to do is now we're going to substitute in the 2.323 in for x for H2 and I2. But notice whenever we do that, that means we're going to get a negative number, and we can't have a negative concentration for H2 and I2. So that means we're going to not use that number, reject it, because it's not chemically meaningful. So that means for x, we're going to use the 0.935 and substitute that in. That works, and that will give us the correct molarity for H2 and I2 and HI. Now, we only have to do this if we are only given the initial concentration and K value. This is when we're going to have to work it this way and use the quadratic equation. Otherwise, if you're given the initial and final, just use your ICE table like we did in the previous section. It's not as difficult, and you don't have to use x in the quadratic equation. I really don't think that this is going to be on the AP exam, but I just wanted to go over this example so you have kind of the backing to it, okay?